Hey, nice to see you again. Welcome to section 2.2, the derivatives of vector functions. The goal of this section is to study the derivative of a vector function and to interpret this derivative as the tangent vector on the function's graph. To be able to talk about derivatives, we need to talk about limits, and while we're talking about limits, we may as well talk about continuity, although very briefly because we want to get to the definition of derivative as quickly as we can. So the definition here, 2.2.1, the limit as t approaches a can be either a finite value or an infinite value, of a vector function r of t, which has got component functions f1 of t, f2 of t, and f sub n of t, is defined component-wise. And what that means is the limit as t goes to a of r of t is the limit as t goes to a of the first component, and the limit as t goes to a of the second component, all the way up to the limit as t goes to a of the last component. So the limit as t goes to a of r of t exists if and only if each of the component limits exists. So very quickly then we can talk about continuity. Definition 2.2.1. A vector function r of t is called continuous if and only if the limit as t goes to a of r of t is equal to r of a. So now that we have an idea of what limits are for vector functions and how to calculate them, we can go directly to the definition of the derivative. So definition 2.2.3, the derivative of a vector function r of t is defined as r prime of t is the limit as h goes to 0 of r of t plus h minus r of t all over h, if this limit exists. And if this limit exists, the function, the vector function, is called differentiable. Now this limit probably looks familiar to you from your calculus course. It should. And the only difference really is that this is not a real valued function, but a vector valued function. And so theorem 2.2.1 says, well, practically speaking, how do we calculate the derivative? Do we really have to do this limit every time? And luckily the answer is no. So if r of t is this vector valued function with components f1, f2 up to fn, where those functions are differentiable, that means their derivatives exist, then r prime of t, the derivative of the vector valued function, is the derivative of each of the component functions. So let's go and just do that proof really quickly. So we have r prime of t, by definition, is the limit as h goes to 0. I'm just recopying the limit that is 1 or 2 centimeters above me on my page here. R of t plus h minus r of t over h. Now these are vectors, so let's write this subtraction as components. So I've got the limit as h goes to 0. I'll bring out the 1 over h as a scalar. And we've got the first component, f1 of t plus h minus f1 of t. And we have that all the way up to the last component as well, f sub n of t plus h minus f sub n of t. That's what vector subtraction means. Now we know we can bring the scalar, and the definition of the limit tells us we can bring in the limit as well. In other words, we have the limit as h goes to 0 of f1 of t plus h minus f1 of t all over h. And you have that for each of the components. So we have that all the way up to the limit as h goes to 0 of f sub n of t plus h minus f sub n of t over h. Now these functions are differentiable, which means that each of these limits exist because they are the derivative limit and they are equal to the derivative of those component functions. So we have f prime, f sub 1, that's hard to say, f sub 1 prime of t all the way up to f sub n prime of t, and that is exactly what we were asked to show. So let's just do a little example quickly here. So example 2.2.1, we're given r of t is secant of t tan of t cubed and t squared, and we're asked to find r prime of t. So this is really just an exercise in our derivative rules from our Cal 1 course. So we have r prime of t is equal to, well, it's equal to the derivative of each of the component functions. So the derivative of the secant, the derivative of tan of t cubed, and the derivative of t squared. So if we remember our derivative rules, the derivative of secant is secant tangent, so secant t tangent. T, we're going to need a little chain rule here. So the derivative of tangent is secant squared t. We're going to keep the same inside function, so it's t cubed, and then we have to multiply that by the derivative of the inside function, or 3t squared. And lastly, polynomial derivative of t squared, 2t. And that is it for calculating the derivative of a vector-valued function. Now, calculating it is one thing, interpreting it is another. And that's what we'll do in the next video, is section 2.2.3, the interpretation of this derivative graphically.